I'm going to continue the class with an example of root locus with complex number that will actually showing you the step number 8. Okay, so let's say we have this example of a problem. In this case, you have a controller, you have your system, and your feedback is a H with value of 1. If you have H here is value of 3, for example, class, so you need to put the kgh, you need to include the value of H. Normally, I'm using 1 to make it easier for me to calculate. But in your case, for example, if you have in your exam, in your test, H is not 1, then you need to calculate them, all right? Okay, so for this particular problem, you're going to start with step 1, which is you need to find your kgh. You equate 0. What is this? This is your open loop system, Open loop transfer function. Okay, so that is actually K over S, K multiplied by S plus 4 by S squared plus 2S plus 2, and that's S then. Okay, so that is your kgh. You don't need to equate this, sorry. Okay, so that is your kgh. Okay, so from there you find your numerator S, you equate with 0, that shall give you your 0. In this case, you will see that there is a 0 element because you have S there. So that will give you your roots. So S is equals to minus 4. That is your 0. So 0 is equals to minus 4. Number of 0, which is Z, I use is equals to 1. So it means I have 1 Z. And then denominator S equal with 0. You're going to have S is equals to 0 for this part here. And for this part, it will contribute a complex and conjugate. Okay, so that will give us S, if I find S squared plus 2S plus 2, if, this is equate this with 0, you will have 2 complex number. Okay, so this one can be obtained by finding the quadratic equations of this. Okay, so sama juga kalau let's say rather than giving you transfer function, let's say the problem is not giving you transfer function, but they give you your roots. Okay, so if they give roots, these poles and 0, then you can also from poles and 0 convert it into transfer function. It's the same thing. Okay. Right, that's step number 1. You need to complete by sketching the poles and 0 on your S-plane. S-plane diagram. So as I mentioned, for plotting in S-plane diagram, you need to use your graph paper. But while you're doing your solution here, you just sketch first so that you can know how does the locus look like. But the moment you already sketch everything, you can then plot it on your graph paper. And when you plot on your graph paper, make sure the scale that you use is the same. For real axis and for your imaginary axis, the scale is the same. Means to say, if it's using 1 centimeter for 1 unit in your imaginary axis, similarly in your real axis, you need to use 1 centimeter for 1 unit. Okay. Okay, so in this case, I have poles. Let me use red color. I have poles with a cross. Poles, you must use cross. For 0, you're going to use circle. Okay, so for -1j, it's here. Okay, my video is a bit delayed. Okay, so that is my complex, and it's known as complex and conjugate. So because one of them is having positive value, the other one will follow with negative value. And as I mentioned in my previous video recorded session, I've mentioned to you that when you plot root locus will have a mirror image along the real axis. So if you look at the real axis, the top and the bottom, it will look the same, the mirror image look. Okay, so The way your root locus looks like also will be mirror image. Okay, and then don't forget you have 1 0 just now at -4, so that 0 will be a circle. Okay, I'm going to use circle. Right, then that is your step number 1. For step number 2 is just identifying where is the location of your locus. So the step number 2 says to the left of odd number of locus on your real axis. Sorry, to the left of odd number of element on your real axis. So you look along your real axis. Then if you have any element, for example, poles and 0, or if you have any poles and any zeros again, you're going to look at to the left of the odd, there will be locus there. So in this case, this is the first element. Okay, your poles is the first element. To the left of your poles, there will be your locus. Okay, so and where does the locus go? Until the next element. So in this case, until your pole at -4. Okay, so then this poles, this 0 and number 4 at -4, this is another element. This is the second element. So to the left of the second element, there will be no 0. Okay, so in this case, I'm going to have root locus here. That's it. So in this case, only one root locus will be on the real axis. But of course, I remember that there's another pole here and another pole here. For the complex pole, there will be locus as well for the complex poles. But it's not going to be on the real axis. So we need to find how does that locus on your complex poles behave. Okay, so this is step number 2. So I can just write down step 2. Region of locus. Okay, so that's it. And then you write down your step number 3 if you like. This is sometimes you can just keep in your mind. You know there will be 3 locus. Open OL is open loop, open loop poles, and one will end at 0. Why only one end at 0? Because you have only 1 0. If you have 2 0, then 2 will end at your 0. So the one that will end at your 0 depend on number of 0 that you have. Okay, so that is just to show you how many locus that you're going to have. You're going to have 3 locus for this particular example. 3 locus because you have 3 poles. So you have 3 locus, 1, 2, 3. Okay, and then one of them will end at 0. So looking at the diagram, you know already which one that will go to the 0, isn't it? Because this is, there's a pole here and there's a 0 here. So definitely the locus will start from these poles and then it will go towards the 0. So that is the first locus that you're going to have. Okay. And then the other 2, you need to find the angle of asymptote for the other 2 locus. Right. So that will be step number 4. Because you know the other 2 will go to plus minus infinity. So you need to find step number 4 to find the angle of asymptote. Okay, and as I mentioned, angle of asymptote, it depends on the number of poles minus number of 0. If your P minus Z is equals to 1, then you're going to have 1 angle of asymptote. If your P minus Z is equals to 2, then you have 2 asymptote. If it's 3, then 3, and so on and so forth. And the formula for it is theta is equals to 2K plus 1 multiplied by 180 degrees divided by P minus Z. So in this case, your P is a number of poles. So how many poles do you have? 3 poles, P1, sorry. P1 is equal to 0. P2 is equal to minus 1 plus J. P3 is equal to minus 1 minus J. Number of poles ada 3. Okay. So in this case, I have 2k plus 1, 180 degrees, divide by 3 minus 1. Okay, because you have 3 poles and 1 0. So divide by 2, 180 divided by 2 is 2k plus 1 multiplied by 90 degrees. So that will give you your angle of 90 degrees and 270 degrees. How do I know this? By giving value of k equals to 0. For this formula, there's a k there. So you need to put the value of k equals to 0, k equals to 1, k equals to 2, for example, until you repeat the same angle. And how does the asymptote look like? I've already shown in the previous video. It will look like a okay, for 90 degrees, it goes up like that. Okay, so this is 90 degrees. And then for 270 degrees, it goes down like that. Okay, so it's like a straight line for this particular example. Okay, then step number 5 is for you to find out where to place this asymptote. Okay, so that is alpha A. And the formula is some value of poles minus some value of 0. Divide by P minus Z. Okay, so that's 0 plus minus 1 plus J plus minus 1 minus J minus what? You have 0, isn't it? And that value of 0 is minus 4. Okay, so this whole lot divided by your P minus Z, which is 3 minus 2. 3 minus 1, sorry. Okay, so if you look at here, you have minus 1 plus minus 1, that's minus 2. Minus 2 and this minus and minus become positive 4. So minus 2 plus 4 is positive 2. Okay, positive 2 means your pole or your asymptote will be on the positive real axis. It will actually be in the positive side. Okay, and then we'll divide by 3 minus 1 is 2. It will become 1. Can you check this if it's correct or not? And this, you can see this one, plus J and minus J, it will cancel each other. Okay, so you have plus J and then you have minus J, right? So that will actually become 0. Okay, so you don't have that J value. It will not contribute anything to your angle of your asymptote. Let me check again. Minus 1 is minus 2. Minus 2 plus 4 is 2. 2 divided by 2 is, 3 minus 1 is 2. 2 divided by 2 is 1. So this is where your asymptote will be. So it's actually going to be at positive side. So if I have this, let me just copy again this one. So basically, I know already that my asymptote will be 90 degrees and 270 degrees. And it will be at minus 1. Positive 1. On my real axis, it will be positive 1. That is my asymptote. Okay, so I know now that actually what happened, this locus will go to that direction and this one will go to that direction and follow the asymptote. Okay, sorry, my video is a bit laggy. Okay, so you need to know now if this one goes up and this one goes down. Of course, you need to know the crossing at the imaginary axis. Where does it cross on the imaginary axis? Okay, so in this case, guys, you do not need step number 6. Okay, step number 6 does not require here. Why? Because step number 6 is a breakaway point. Breakaway point is when your locus poles and poles are meeting each other and they are leaving the root locus. So in this case, you do not have that situation. Breakaway point is not needed for this. Anybody do not agree with me on that? Step number 6 not needed. Okay, so step number 6 is not needed. There's no breakaway point. So I just put in a bracket here. Breakaway point will happen something like this. When you have locus when you have poles and poles, and then when you do your step number 2, your locus is within the 2 poles. So therefore, you're going to have poles are going towards that direction, and the other poles going towards the same direction. So you will have breakaway point, sigma B. Okay, in this case, you don't have sigma B, you don't have that situation because you don't have poles that is actually meeting each other like that. Okay, because this pole here is meeting 0. Poles, when it goes to 0, it will end at 0. That's it. Okay, no need to break away from 0. Okay. All right, therefore you go straight away to step number 8. Okay, this is the important part which I've not shown you before. So step number 8 is what we call angle of departure. So angle of departure is given by theta d. Okay, so the angle of departure, the formula is 80 degrees minus sum of angle. Okay, so that is the formula. But what is sum of angle? So I'll show you that if you have angle, sum of angle, it is sum of any positive angle coming from your poles minus any angle coming from your 0. Okay, so if you have any angle coming from poles, it will minus by angle coming from 0. So how do we do that? Okay, let me just show you how to get this angle. That is why you need to plot on the same scale, because you need to sketch it. Sketch it nicely. Because you need to draw nicely. Okay, so the situation just now, if I enlarge this, I have 1 here at 1, and then 1 here at -1. Okay, so that's your poles. Color line sikit lagi. And then you have another pole at 0, kan? And then another 0 at -4. Somewhere there. Okay, let's say I want to know angle of departure at this positive side. Okay, the positive complex poles here. Okay, so if I want to know that angle of departure from there, what I want to do is I will take this angle, these poles, I will connect with all other poles and 0. Okay, so that is how I connect to them. Then the angle of departure is actually this angle here. From horizontal to that, there is theta 1. Okay, from horizontal to that, that's theta 2. Then from horizontal to that is theta 3. Okay, so angle of departure will be your sum of angle will be all the positive angle coming from poles. So theta 1 plus theta 2. Why? Because it's poles to poles. So you contribute positive angle. From poles to poles, positive angle. Okay. Some from poles to 0, the theta 3, that will give you negative angle. Is that okay? Right, so basically we need to take the protector and measure this, or you can use your algebra to measure this. Can you help me on this? What is theta 1? I know this is 1 and 1, so therefore this angle here is 45, isn't it? Can. So 180 degrees minus 45 is 135. Betul? Can somebody check for me, please? 135, kan? Okay, so that is 135. Hang on. Your theta 1. Okay, what about this theta 2? This is 90 degrees, isn't it? Theta 2. Okay, what about theta 3? Can you find using Pythagoras or not? So this is -4, this is -1. So this length here is 3. Okay, betul tak? Okay. So from -4 to -1, so this is 3 unit, 1, 2, 3, and this is 1. And can someone find for me that one? Angle is a opposite divide by adjacent. Theta, apa tu? Tangent of opposite is 1. This is 1 over 3. Tangent tu kan? Opposite over adjacent. Can somebody find for me theta 3, please? Nampak. Oh, 13.43. 13 ke 14? Ke 18?
18.
18 Alif, Mohamed, check again Maybe it's wrongly calculated. Okay, so that is 18 degrees. Oops. I'm going to use 18 degrees. I'm not sure if it's correct or not. You guys have to check again So actually you can use Pythagoras to find it. So 18.43 degree. Okay, so that is your sum of angle. So 135 plus 90 is 225 minus 18.43. That's going to give us positive 206.57, isn't it? Okay, so that is not your angle of departure. Your angle of departure is given by apa? 180 degrees minus that. Minus 26.57 degree. Okay, so how to plot this angle of departure? This angle of departure is happen on your poles, on your positive poles, okay, because you calculate from the positive pole just now, isn't it? So it will happen on your positive poles, okay? So let me just copy this again. So angle of departure will come from your poles that you calculated just now, the positive complex poles just now, okay? So the angle of departure will be defined like this. Let me use purple. It's negative 26. So is if positive is from horizontal counterclockwise. So negative must be from horizontal counterclockwise. Sorry, kebalik. If it's positive, is coming from horizontal counterclockwise, kan? So if it's negative, it's coming from horizontal counterclockwise down there. Okay, so that's your angle. Macam itulah lebih kurang 20, negatif 26.57. Okay tak? Okay, that is your angle. Okay, so then you remember you have your your asymptote just now dekat positive 1, right? So that's your asymptote. So basically what happened, your locus will leave your poles from the center of your poles. It will leave following the negative 26.25 ni. 26.57 ni. Dia macam tu. Okay. And then baru dia pergi ke asymptote. And then naik macam tu. Okay. So another important point that you need to find is this crossing at your imaginary axis so that you know how long dia nak turun bawah before dia naik atas. Okay, is that alright? That is your angle of departure. Because your complex number will actually leave the poles following the angle of departure. So in this case, it's negative 26.57. Okay, angle of departure, you only need to calculate once. If your angle of departure, you calculate using your positive complex poles, okay, it will give you negative 26.7. So it means to say the other angle of departure, because you have two angle of departure. So angle of departure 1 is negative 26.57. Therefore, straight away, angle of departure 2 will be the positive value. Let me just move this slightly down. Angle of departure 2 will be the opposite value of this, because you remember your locus is a mirror image. Okay, so the second angle of departure, you do not need to calculate anymore. We'll just have the positive value of your angle of departure. So kalau yang atas tadi negatif, yang bawah akan jadi positif. So again, the way we do it is we take our protector letak sini, and then positive 26 will be from horizontal to counterclockwise. So like that. That one is exaggerate lah, negative 26, not much kan? Pardon. Okay, it's like that, positive 26, 57. Okay, so basically for your angle at this complex number, you will start from the center of your poles, and then it will follow this angle before it cross your imaginary axis, and then follow your asymptote. Okay, so it will never cross your asymptote, but it will follow very closely to your asymptote lah. Okay, so that is why another important point that you need to find is this crossing at your imaginary axis, so that you know how long your poles will follow your angle of departure before it cross your imaginary axis. Okay, so if it's actually 26.57, it looks like this, positive. If it's negative 2.57, it looks like the bottom one lah, with negative value. Okay, any questions on this? So your locus will look like this. Of course, don't forget the first post is just from post to 0 like that. And then for root locus, you need to show the arrow. Why? Where the direction goes. Why? Because root locus is a vector, it's a direction. Okay, so you need to show the arrowhead, where does it go? If you just draw a line, that's not locus, it's a line, isn't it? So for the bottom, the first locus just now, from post to 0, you need to show the arrowhead, like that, it's moving. Okay, so similarly this one, this is moving from post to infinity, and the other one is from post to negative infinity. Is that okay? That is step number 8. Okay, so if I just show back again, step number 8 is finding angle of departure. Okay, and angle of departure is given by this following formula. Okay, theta d is equals to 180 degrees minus sum of angle. And this sum of angle, if you have poles to poles, it will contribute positive angle. If it's poles to 0, like this one, and poles to 0, so this will contribute a negative angle. Okay, so in this case, how do I measure the angle? Horizontal to the vector, from that poles to the other poles, from that poles to the other poles, from that poles to that 0. Okay, so the angle is like that. Is it okay? Right, once you have found the angle, you can use Pythagoras, you can use your protector, you can find the angle, then you do the sum of angle. Then after you find the sum of angle, of course you need to minus, have the 180 degrees minus that sum of angle. And then you're going to get two angle actually, because theta d, there will be two values. One is the one if you find from this top and poles, then if it's giving you negative value, then the bottom poles will give you positive value. You do not need to calculate twice. You only calculate once. Okay, so you just do the opposite sign of it. Okay, and that is how your angle of departure looks like. Okay, so it's actually following from horizontal to the position, either positive or negative. So it depends on your angle of departure. That's it. Okay, so this is for step number 8, how your complex poles leave its poles going towards infinity. Okay, then step number 9, I need to find this. I need to find the crossing at imaginary axis. Okay, let's do that. Okay, to complete this example. So for step number 9, please don't forget to use root array. Root array. Okay, what do you want to do? To find the crossing, the coordinate of the crossing at imaginary axis. If you have, So step number 9 is also optional. Okay, so if you do not have the imaginary axis, crossing imaginary axis means to say, let's say your asymptote is not here. Your asymptote is not on the positive side. And your angle of departure also in the opposite sign. So your locus, maybe your angle of departure is having a positive sign. So your locus will go and follow this asymptote like that. Okay, so you are not going to cross at your imaginary axis. So if that is the case, you don't need to find your imaginary axis. But in this case, you have it here, so you need to find imaginary axis. Okay, so the formula is you need the method of doing this, we need to start with kgh plus 1. 1 plus kgh. 1 plus kgh equals to 0. That is your characteristic equation. Okay, so there's 1 plus ks plus 4 over s squared plus 2s plus 2 equals to 0. If I expand this, okay, cross multiply, it becomes s squared plus 2s plus 2 plus ks plus 4k, isn't it? If I expand that, that is 0. And the denominator disappeared. Why? Because it will be multiplied. This denominator, if I bring to the other side, it will multiply with 0, so that's gone. Okay, so this one will become s cubed plus 2s squared plus 2s plus ks plus 4k equals to 0. Right, if you look here, for s to the power of 1, there are two values. You have 2 and k. So you need to actually collect it together. So that will be s cubed plus 2s squared plus 2 plus k. S plus 4k equals to 0. All right, is that okay? Then from here, we draw our root array. Started with s to the power of 3, s cubed, then s squared, s1, and s0. So I have 1 here because of this coefficient. I will skip 2, I will go to the other one, so that's 2 plus k. Okay, and then if I skip this one, okay, from here I skip this one, I go to the other one, this not gone, nothing, there's 0 there, so I don't need to put. Okay, so this is 2 here. Why? Because coefficient of s squared. Then I will skip coefficient of s1, I'll go to coefficient of s0. So 4k is actually coefficient of s0. Okay, so that's how you fill the first 2 rows of your root array. Okay, and then the next row, you need to do the calculations. Okay, so I have 2 multiplied by 2k minus 1 multiplied by 4k. Okay, again, 2 multiplied by 2k plus, 2 plus k minus 1 multiplied by 4k divided by 2. So that will be okay. So is that it's 4 plus 2k minus 4k divided by 2. Okay, so this one will be 0. Why? Because it's 2 multiplied by nothing, isn't it? Minus 1 multiplied by nothing, so that will be 0. If this is 0, guys, this here straight away going to give you 4k. Why? Because this one multiplied by that, by 4k, minus 0, divide again by this value. So you're going to have 4k only. Right? So that's here. All right, so as I mentioned, that if you want to check if the system is actually stable or not, we're going to look at our first column. If it's all positive, this is positive, 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 these are all stable. Okay, but I'm not going to find when it is stable, isn't it? I want to find when it is critically stable. This is the point where it is critically stable. Okay, so if it's stable, the value will be positive. If it's unstable, the value will become negative. Okay, so the value here, not the value of your coordinate. Okay, so if any one of these is negative, then it becomes unstable. But I want to find when it is actually critically stable. So I need to equate this element to 0. This is already 1, so it cannot be 0. The second one is already 2, so it cannot be 0. But the third element and the fourth element, we can make it 0 because it depends on the value of your k. Okay, so for the first one, if I go for 4k, if I take 4k equal to 0, that will give me k equals to 0. But this is not the position that I'm actually looking at, okay, because k equals to 0 is a starting point of your root locus. Okay, so that will be maybe because of this pose that you have in this 0 here, okay? But not this one. This one, your k cannot be 0 at that point, at your crossing immediate axis during, in the middle of the locus, okay? At the middle of the locus, k cannot be 0. Why? Because k is already 0 at the beginning of your locus. So when you increase the value of k, it starts to move in. So of course, in the middle of the way, k cannot be 0. Okay, so then we ignore this one, okay? So you go to the next value, which is 2 plus k minus 4k divided by 2. So what do you get? So I have 2k minus 4k. That's minus 2k. 4 minus 2k divided by 2 equals to 0. That's going to give me 2, k equals to 2. So you see, even with k equals to 2, your system is about to become unstable. It's critically stable, right? So the moment it is something more than 2, for example, 2.1 also, your k, so your system is already become unstable, okay? So how to know where is the coordinate? So I know now, at this point, it will cross my imaginary axis at k equals to 2. But I need to know the coordinate, isn't it? So in order to find the coordinate, either I substitute into my characteristic equation, okay, I will find the coordinate, but I need to know the coordinate in terms of complex and conjugate, because you have on the positive side and also on the real side, it will be complex and conjugate with imaginary value only. Okay, sebab ni real value dia kosong kan, real axis dia kosong. So this is complex complex coordinate with imaginary value only. Okay, so if I solve by solving this characteristic equation, I put the value of k here equals to 2, and then I find the roots, and the complex conjugate is the position that I'm looking for. Okay, so that is one way of solving it. The other way of solving it is by doing this S squared here. I've already shown this in the previous recorded example. Okay, so I'm going to use that S squared there. Okay. So how to use that? This S squared is having coefficient of 2. That 4k is actually for s to the power of 0. So that will give me 2s squared plus 4k. Equals to 0. Then I'm going to use this critical value of k. I'm going to use that k critical and substitute into this 4k here. Right, so I have 2s squared plus 8 is equals to 0. Okay, s squared is going to be minus 8 divided by 2. So that's minus 4. Okay, and then that minus 4, if I find the square root, it's going to be plus minus square root of minus 4, isn't it? Okay, so I can change that square root of the magnitude of minus become j. So just square root of 2. So s is going to be plus minus j. 2j. Okay, so the coordinate here is actually 2j and apa ni 2j and minus 2j. Okay, so you see I am actually making a little bit of mistakes there by thinking that it is less than 1, isn't it? Nampak tak? I thought in the beginning it's going to be something less than 1. Actually, no. Actually, the value is 2. So we need to replot this. That's why when you sketch, that's not necessarily your final solution. So you need to sketch again the correct one. And then you sketch on your graph paper. I already shared the graph paper in your apa ni? WhatsApp group, and also I put it in your e-learning. Okay, so if you want to actually print it so that during the test, during the exam, you can easily use it. Okay, I'm just doing a rough estimation. In your case, you need to sketch this on your graph paper, so yours will be more accurate, of course. Okay, so my pose is here, my 0 is here, and then have another pose here, another pose here, and then I have my asymptote at 1 just now, isn't it? So that's my asymptote. And I know my angle of departure is negative 26 point something just now, point berapa tadi? 26.57, 26.6 lah. Okay? And then it will cross my angle at 2j and minus 2j. It will cross my imaginary axis. Okay, so that's my imaginary axis, my asymptote. So how does my locus looks like? It will leave with negative 2.6 and it goes straight away to this. Go directly to my asymptote and then follow my asymptote. Okay. Similarly, this one, we go positive first. Remember, positive 26.6 goes down, cross at minus 2. Okay. Go very close to asymptote and then follow the asymptote. Not too close. And then don't forget your arrowhead to show the motion. Okay, and don't forget there's one more locus here. So this one, if you have your graph paper ready, when you already find all these value, you need to sketch it on your graph paper. Okay, is that all right? That's how my root locus looks like. Okay, so I can, if you like, you can put here the value. Angle is theta D, is theta D1, is theta D2. Okay, so it's actually equals to whatever the value that you have calculated is now. Okay, so that's how your root locus looks like for this particular example with your angle, with your complex pole. So no matter what is your complex pole, this is the method that you're going to do, right? Sometimes you need, let me just move this a bit. Sometimes you need to have the breakaway point if the drawing require a breakaway point, okay? But for this particular example, no need, okay? So that's very straightforward. Okay, question can also be the other way around. Given zeros and poles, you need to plot your graph. Okay, so if you're given the zero and poles, it's the same. You can use the zero and poles and then obtain your transfer function.
Doktor.
Yes, Ayah.
Boleh estimate balik ke yang 2s square plus 4k equal to 0? Macam mana boleh dapat?
2s squared plus 4k. Okay, sebenarnya macam ni. Once you already find your critical value of k, either you masukkan balik dalam characteristic equation and then cari location of this position of these two coordinate. Okay, so these two coordinate, when you solve your using your characteristic equation, you substitute the value of k. This is quadratic equation, right? And this is cube equation. So you're going to have 3 roots. Okay, so the 2 conjugate roots with imaginary value only, that will be your location here. You definitely going to have that. But you akan jumpa satu value lain lah yang you akan ignore that value because that one doesn't mean anything. Maybe there's some other values that is not this, not what you want. Okay, that's one. Okay, but the other way around, you can also use this S squared quadrant here. Okay, so how I do that? I'm just going to know that this is S squared. So this is the coefficient of S squared. This is 4K is the coefficient of S0. So if I use this, the coefficient, it's the simplification of my characteristic equation. Okay, so I will take that and I write in this form. 2 plus 2s squared, because I know this is 2 is actually coefficient of s squared. This 4k is coefficient of s0. So 2s squared plus 4k equals to 0. Okay, and then I solve it for s. Okay, is that right?
Okay.
Okay. So boleh juga kalau kau nak buat macam ni, yang ni paling senang lah. Paling senang you buat this simplification of your characteristic equation. But if you want to know the long way, is actually basically substitute back in your characteristic equation and find the coordinate. Okay, but when you solve this characteristic equation, because this is S cubed, so your characteristic equation will give you 3 roots. Okay, so the roots that you're going to choose is the one with complex and conjugate with imaginary only. Because this one there's no real kan, yang ni imaginary saja sebab real dia kosong. Okay, so that's also going to give you the same value.